Welcome. Today we're going to take a journey, a deep dive into the architecture of logic itself. We're going to see how it's intentionally broken, how we can build it to be incredibly resilient, and how it can sometimes break itself in the most mind-bending ways imaginable. All right, so here's the plan. We'll start in familiar territory, the world of bad arguments. Then we'll look at how to build systems that actually work. And finally, we're heading into the deep end with paradoxes that push logic right to its absolute limit. So let's kick things off in a world we all unfortunately recognize, the world of flawed arguments. The kinds of arguments that aren't designed to be right, they're designed to win. It seems like a simple question, right? What makes an argument bad? Is it just about getting the facts wrong? Well, it's actually a bit more complicated than that. You see, a logical fallacy isn't just a simple mistake. It's a fundamental error in the structure of the reasoning. And here's the key. These errors are often not accidental. A lot of the time, they are specifically designed to be super persuasive, to get you to agree even when the logic is totally broken. Okay, so take a look at this. At a glance, they look almost identical, don't they? On the left, you've got a perfectly valid argument. But on the right, there's this tiny, sneaky error. It's called denying the antecedent. It's where you wrongly assume that just because the if part didn't happen, the then part can't happen either. It looks so similar, but its structure is completely busted. Let me show you why. And this is a perfect example of the flaw. I mean, look at it. Premise 1, if he was hit by a meteorite, he's dead. True. Premise 2, he was not hit by a meteorite. Also true. But the conclusion, therefore Socrates is not dead, is obviously false. He's definitely dead for other reasons. This proves the argument structure is garbage, because good logic can never ever lead you from true statements to a false one. But it's not all about these formal errors in logic. We've also got informal fallacies, which are, honestly, much more about playing with your head. Think about propaganda films like Triumph of the Will. The actual arguments being made are pretty weak, but the context, these massive rallies, the spectacle of it all, makes it incredibly powerful. The goal isn't truth, it's persuasion, and it uses awe and emotion and a masterful delivery as rhetorical weapons. All right, so we've seen how easy it is to break an argument. Let's flip that on its head. How do you build a logical system that doesn't break? How do you design a set of rules that's strong, clear, and can actually adapt to change? And this brings us to a really cool idea called active coherence. The goal here isn't just to build something stable that sits there and never changes. No, it's about building a system that can stay whole while it's constantly managing change and new information. Okay, this is a fantastic example of that idea in action. It's a system that takes chaotic computer data and turns it into music. The logic is crystal clear. A security alert automatically triggers a tense minor key. When the issue is fixed, it resolves to a calm C major chord. You can literally hear the health of the entire system in real time. It's brilliant. But check this out. It's not just a one-way street. The system is designed to adapt to the person using it. So a soft touch on a controller gets you a perfectly structured musical scale. But if you press down hard, the system gets the message. It backs off, it yields control, and it allows for more creative, emotional expression. The logic itself is adaptive. Now, this whole idea of resilience isn't just for artsy stuff. It's absolutely vital for things like security governance. It's built on 3 pillars: a framework to predict risk, an engine to control what's happening, and, this is the real secret sauce, a planned, intentional way to tear things down and change. True resilience isn't about being rigid. It's about having a built-in mechanism for self-correction. So we've seen bad logic, and we've seen good, resilient logic. But what happens when the rules themselves, even when you follow them perfectly, are what breaks everything? Well, welcome to the weird and wonderful world of paradox. So let's start with a classic thought experiment, Hilbert's Grand Hotel. I want you to picture a hotel with an infinite number of rooms. And here's the catch. Every single one is occupied. The hotel is completely full. Can it possibly take on any more guests? The manager has this brilliantly simple, totally logical plan. He asks every guest to please move from their current room, let's call it room N, to the room that is double that number. So the guest in room 1 moves to 2, the guest in 2 moves to 4, 3 moves to 6, and so on, forever. And boom! Just like that, all of the odd-numbered rooms, 1, 3, 5, 7, all the way to infinity, are now completely empty. The hotel that was totally full has just created an infinite number of vacant rooms. This is the bizarre, head-spinning logic of infinity, where a piece of something can be just as big as the whole thing. This idea isn't new. The ancient Greeks were totally obsessed with this stuff. The philosopher Zeno argued that to cross a racetrack, you have to complete an infinite number of smaller tasks. You have to get halfway, then to the quarter point, then the eighth, and on and on. His logic seemed to prove that you could never even start moving. And that brings us to the big one, the paradox that literally shook the world of mathematics to its core. It was discovered by Bertrand Russell back in 1901, and it showed that even the simplest, most obvious logical rules could create an inescapable contradiction. Okay, to get this, we just need to get our heads around two really simple definitions from set theory. First, we have normal sets. A normal set is just a set that doesn't contain itself. For example, the set of all squares is not itself a square. Easy enough. Then you have abnormal sets, which do contain themselves. Seems pretty straightforward, right? Okay, you with me? Normal sets don't contain themselves. Now, here comes the question that breaks everything. Let's create a special set, and we'll call it R. And the definition of R is super simple. It is the set that contains all of the normal sets. That's it. So, the big question is, where does R itself belong? Is R normal or is it abnormal? And here is the logical trap. Let's walk through this. Option 1, let's say R is a normal set. Okay, well, by its own definition, R has to contain all the normal sets. So if R is normal, it has to be inside itself. But wait, a set that contains itself is abnormal. Okay, scratch that. Let's try option 2, R is abnormal. Well, the set R is only supposed to contain normal sets, so if R is abnormal, it can't be a member of itself. But a set that isn't a member of itself is normal. Do you see the problem? Either way you go, the logic forces you into the exact opposite conclusion. It's a perfect contradiction. And I want to be clear, this wasn't just some fun little brain teaser. This was a bombshell. This quote from the great mathematician Gottlob Frege says it all. He got a letter from Russell with this paradox right as his life's work was about to be published, and he realized that this little problem threatened to bring down the entire foundation of mathematics. Okay, let's take a breath and try to pull all of these wild threads together. What can we actually take away from this journey through flaw and function and paradox? So what's the big picture here? Well, first, that flawed logic is everywhere, and learning to recognize its structure is basically a form of self-defense against manipulation. Second, the strongest, most robust systems aren't the most rigid ones. They're the ones built to adapt and even tear themselves down to improve. And finally, that even our most perfect systems of logic have these strange, beautiful boundaries, paradoxes that reveal deep truths about our world. And that really leaves us with one last big question to chew on. If the pure, clean world of math and logic can contain these incredible, self-collapsing contradictions, what happens when we turn that same intense scrutiny on the much messier, more complex, and often unexamined systems of belief we use to navigate our own lives?